At this exact moment, people are reading and changing the same database rows. One person opens a checkout page, another person buys one of the items. The inventory row says 12 lamps are in stock. A writer changes that value to 11. Which number should the first transaction see? The newest one? Not necessarily. A busy database can let one transaction keep reading 12 while a later reader sees 11 after the writer commits. Both results can be correct. They are correct for different views of the database. The mechanism is called multi-version concurrency control, MVCC. It is how databases let readers and writers overlap without turning every row into a waiting line. To understand it, we're going to follow one reader and one writer as the same row splits into two versions. Start with a one-copy locking design. Keep one mutable value for the row. Then protect reads and writes with conflicting locks. If a reader holds its lock, the writer waits. If a writer holds its lock, the reader waits. The result can be correct, but under load, the wait queue can dominate response time. A long report holds read locks while an order tries to update the same rows. More work piles up behind those locks. MVCC changes the trade. Instead of forcing every transaction to share one visible value, the database preserves a path to older values while it creates a newer one. The reader does not need the writer's unfinished state. It can keep using the version that was valid for its own view. The writer can continue building the next version. Now, the hard problem is not who gets the row first, it is which version is this transaction allowed to see. Meet reader R100. That is our label for the reader. It starts a transaction using repeatable read. When its first read begins, the database gives R100 a snapshot. That snapshot is not a full copy of the database, and it is not necessarily a wall clock timestamp. It is a visibility rule. The rule separates transactions committed before the view from transactions still in flight. It also excludes transactions that begin later. Our original row, stock equals 12, was created by transaction 40. Transaction 40 committed before R100's view, so 12 is visible. Now writer W104 changes the stock to 11. Before W104 commits, its new version is not visible to an ordinary read from R100. Then the writer commits. A new reader can see 11. R100 still sees 12. Its repeatable read snapshot did not move when the writer committed. The commit changes what a new reader can see. R100 keeps the view it already has. There is one useful exception. A transaction can see its own earlier writes. The snapshot controls what it sees from other transactions. PostgreSQL makes this idea fairly literal. An update creates a new row version. PostgreSQL calls each physical version a tuple. The old tuple says stock equals 12. Its xmin value is 40, the transaction that created it. When transaction 104 updates the row, the old tuple is marked with that transaction's identity, and a new tuple appears with xmin 104. These transaction IDs are visibility metadata. They are not dates on a clock. R100 checks the transaction IDs on each version. It uses their commit state in its snapshot to decide which tuple is visible. Transaction 104 falls outside R100's snapshot, so the newer tuple is too new for this reader. R100 selects the older tuple and gets 12. A reader that starts after 104 commits, can select the newer tuple and get 11. The row did not change into one globally visible value. PostgreSQL kept enough state for each reader to make the right visibility decision. That PostgreSQL layout is one implementation. It is not the definition of MVCC. MySQL's InnoDB engine can reach an older value a different way. Its current record for the row stores the ID of the transaction that last changed it. It also stores a rollback pointer. That pointer leads to an undo record with enough information to rebuild the earlier row. Suppose the current record contains 11 and carries transaction ID 104. R100 sees that the change is too new for its read view, so InnoDB follows the rollback information and reconstructs 12. PostgreSQL can choose between separate row tuples. InnoDB can walk backward through undo information. The physical representation differs. The question stays the same. Which version belongs inside this transaction's view? When I draw a version chain in this video, that chain means a path through row history. It does not mean every database stores full copies side by side. A snapshot's lifetime depends on the isolation level. Under read committed, PostgreSQL gives each ordinary select a fresh snapshot when the statement begins. InnoDB does the same for each non-locking read, which it calls a consistent read. The first select might return 12, then W104 commits. A second select in the same transaction can return 11. Under Repeatable Read, PostgreSQL fixes the snapshot when the transaction runs its first query or data change. InnoDB fixes it with the first consistent read. Later ordinary reads keep using that snapshot. In our toSelect example, both reads return 12, even after the writer commits. That is the behavior we are tracing with R100. The same isolation name does not guarantee the same behavior. PostgreSQL and InnoDB both use MVCC, but they fix and refresh snapshots at different points. Before you predict what a query will see, check the active isolation level and that engine's snapshot timing. MVCC removes many conflicts between ordinary readers and writers. It does not make all transactions independent. Add a second writer. W104 changes stock from 12 to 11. W108 also tries to sell one lamp from the same logical row. The database cannot let both writers blindly declare their version the successor. W108 may wait for W104 to commit, then apply its sale to committed value 11 and produce 10. Or W108 may fail, forcing the application to retry from committed value 11. A successful retry also produces 10. The exact response depends on the engine's rules for the statement at the active isolation level. Writer conflicts still need locks or retries. R100 can keep reading its visible version while the database resolves that conflict. MVCC separates ordinary reads from concurrent writes. Competing writes still need coordination. There is a deeper limit. A transaction can read a perfectly coherent snapshot and still help produce an invalid final state. Imagine two doctors, Alice and Bob. Both are marked on call. The rule says at least one doctor must stay on call. Transaction A reads the snapshot. It sees Bob on call, so it turns Alice off. At the same time, Transaction B reads the same starting state. It sees Alice on call, so it turns Bob off. The transactions update different rows. There is no same row write conflict to force one of them to lose. Under snapshot isolation, both can commit. Now nobody is on call. Each transaction made sense against its own snapshot, but no one-at-a-time ordering of those transactions can produce this result. That failure is write-skew. PostgreSQL's serializable mode can detect that the two decisions cannot safely coexist. One transaction aborts and retries against the newer state. The application can also lock the relevant rows before deciding, or it can redesign the rule so the database can enforce it with one indivisible write. MVCC gave both transactions a stable view. It did not prove their decisions were safe together. Versions solve a waiting problem by creating a storage problem. After W104 commits, version 11 is current, but version 12 is not useless yet. R100 can still see it. Deleting 12 now would change the results of a transaction already in progress. So cleanup must wait. The database tracks a horizon set by the oldest view that might still need history. When R100 finishes and no other eligible snapshot can see version 12, the old state can be reclaimed. PostgreSQL uses vacuum to remove dead row versions and make their space reusable. InnoDB's purge process can discard obsolete undo history and delete marked records. A long-running transaction holds that cleanup horizon back. The result can be wasted table space or a growing undo history. That old version is not a permanent audit log. It exists because visibility requires it. Once no valid snapshot needs it, MVCC has paid its debt and cleanup can take the space back. R100 read 12. A later reader read 11. Both were correct because each snapshot exposed a different committed version. A B tree can get your transaction to a candidate row. MVCC decides which version it can see. To follow that lookup from the beginning, watch the B tree video next.